Welcome to SAPTECH. Today, we are breaking down the exact mechanics of SAP memory allocation and work process management. Every SAP instance faces the same architectural conflict, providing massive memory to high-load transactions while protecting the host operating system from resource exhaustion. When a user submits a request, the dispatcher takes that request and routes it to an available dialog work process, which then pulls memory from the shared host pool to execute the task. This allocation operates as a deterministic defensive fallback hierarchy rather than a single static block of RAM. We are going to map the exact step-by-step memory pulls for a standard dialog process. Then we will look at how the underlying operating system alters the execution paths for background jobs across Linux versus Windows. Finally, we will deconstruct what happens mechanically when a process exhausts every assigned limit and enters the dangerous private mode. Understanding this strict sequential hierarchy is the absolute prerequisite for effectively troubleshooting ST22 dumps and system hangs without resorting to an OS-level reboot. Let's trace a standard dialog work process. When it receives a request, its first task is to roll in the user context to validate credentials. To do this, it pulls a very small, localized slice of memory from the system. This initial allocation is controlled by the parameter ztta/roll_first. Once the context is validated, if the transaction requires more capacity, the process will exhaust this small initial allocation. It then pulls from the shared extended memory pool, up to the limit defined by ztta/roll_extension. If the user is running a heavy transaction and maxes out that entire extended memory quota, the work process moves to its next fallback. It consumes whatever is left of its remaining roll area. At this exact moment, the work process has completely emptied all of its standard shared and roll memory limits. As a last resort, the work process bypasses the shared pools entirely and begins cannibalizing local OS heap memory. By pulling from the heap, the process is now taking physical memory directly away from the operating system itself. Breaching this final threshold forces the work process to compete directly with the operating system for local physical RAM. That sequence applies to user-facing dialog tasks, but we have to look at non-dialog work processes, like background jobs and spooling. These processes execute a distinct fallback logic because they do not require user context rolling. How they pull memory depends entirely on the operating system. Let's look at the execution path for non-dialog processes running on a Windows architecture. After a small initial roll, a Windows-based background job starts by pulling from extended memory. Only when that extended memory is entirely depleted does it reach up into heap memory. Now compare that to a Linux or Unix environment. On Linux, the architecture forces a complete structural inversion for these workloads. Instead of tapping the shared pool, a Linux background job consumes OS heap memory first, bypassing extended memory initially. It only accesses extended memory after its local heap limit is entirely capped out. Because of this reverse sequence, a runaway background job on Linux pulls physical memory right out of the gate, posing an immediate threat to host OS stability. Basis administrators cannot apply standard dialog troubleshooting methodology here. The underlying OS architecture reverses the entire sequence of memory consumption. Whether it is a dialog process at the end of its sequence or a background job on Linux right at the start, any process that touches heap memory triggers a specific system state. The work process has entered private mode, or priv. Normally, a basis safety net kills runaway queries before they drag a system down, the maximum work process runtime parameter. This limit is typically set to 600 seconds. However, a process in priv mode ignores and bypasses the timeout parameter. It will remain active until the user manually ends the transaction or the memory is exhausted. This creates hourglass mode, where a single process hoards memory and refuses to time out, causing permanent congestion for every other process in the system. To resolve this, administrators must use transaction SM04 to identify and forcefully terminate the isolated rogue session. If the process is left to breach all remaining OS limits, it generates an ST22 dump, specifically TSV tnew page alloc failed. This failure is distinct from standard paging dumps under rdisp/maxfs, which govern application program data rather than user context limits. Modern SAP methodology prevents these rigid allocation hangs through zero memory management, or JMM. JMM removes the need for manual, granular tuning of individual heap and role parameters. Everything is controlled by the master governor parameter, phys mem size. Adjusting this to match your physical RAM automatically scales the sub-tier limits for the entire instance. If an instance restart is impossible during critical month-end loads, Basis admins can still force temporary allocations using the RS memory program. While zero memory management auto-scales these allocation boundaries, crossing into priv mode remains an architectural failure that demands immediate manual intervention. SAP memory allocation acts as a defensive fallback system, engineered to sacrifice individual transactions to protect the host operating system. The path depends on the workload and the OS. Dialog processes move through role, then extended, then back to role before hitting the heap. Non-dialog jobs on Windows use extended memory first, while Linux jobs pull from the heap immediately. Reaching the heap memory threshold has severe implications for system stability. Priv mode neutralizes standard timeout protections, forcing the administrator to clear the congestion manually. For detailed information on these parameters and more Basis resources, please check the detailed information in description of this video. And if you enjoyed this video, don't forget to subscribe to the SAPTECH YouTube channel. Mastering these allocation sequences is what separates reactive troubleshooting